So, I generally like to start this class by talking about the scientific method. And I've included here one of my favorite comics, and so I'll give you a second to take a look at that. So, when we're talking about the scientific method, one of the first obvious questions is, what is science? And I think everybody has a pretty good idea of what science is in some extent, but if I ask you to give a definition, that's maybe harder. And actually, one of the definitions that I really like is the definition of science given by Wikipedia. Right, so according to Wikipedia, science is a systematic enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. And so there are a lot of things there that I really like in that definition. Right, it talks about science being systematic. We build and organize knowledge. And then it's really important in science, right, to have testable explanations. If we don't have testable explanations and we're not making predictions about what's going to happen in future experiments, then it's not really science. Some other definitions or add-ons to that, right? It's an exploration of natural phenomenon. We're looking for understanding, right? We're not just collecting facts. And science often refers to a way of pursuing knowledge and not the knowledge itself. Right? We can take a scientific investigation in lots of different fields that may or may not be generally under the umbrella of what people think about as hard science. All right, so what is the scientific method? I know when I was first taught the scientific method, I was sort of given a list of these 12 different steps, and I had to memorize those steps, and that was the scientific method. I think that's sort of an idealized depiction of what the scientific method really is. I think a better explanation of the scientific method is that it's a flexible process of creative thinking and testing aimed at objective, verifiable discoveries of how nature works. Right? And I think the big thing there is that the scientific method is flexible. Right? When we're actually doing scientific investigations, we don't get out that list of 10 or 12 steps or whatever it was and say, okay, what was step one? Right? So the scientific method is not a concrete thing. But I think there are some common aspects of the scientific method and scientific investigations that we should be familiar with. And so I want to talk more specifically about observations, hypotheses, experiments, laws, and theories. And what exactly are these different components of the scientific method? All right, so the first thing I want to talk about is observations. And I think if you go back and look at lists of the steps of a scientific method, probably the first step in most or all of those is to make observations, to collect information about the world around us and make observations. And so I think the idea of observations is pretty straightforward, but there is one aspect of observations that I do want to mention. And oftentimes we break observations down into two types. There are qualitative observations and quantitative observations. Right, and so qualitative observations are descriptions about the characteristics or behavior of nature. Right, and so colors are a good example of a qualitative observation. And we contrast that with quantitative observations where we're comparing it to a standard numerical scale. And that would be a quantitative observation. So if I was to say, this book is 12.5 inches long, that would be a quantitative observation. And if you notice, oftentimes with quantitative observations, they involve numbers, and they almost always have units, right? So I couldn't say this book is 12.5 long, right? Because that leaves out a very important piece of information. 12.5 what? Inches, centimeters, feet, mile, light years? And so whenever we give quantitative observations, we almost always have to include a unit with that. Okay, so observations really tell us what's going on around us. When we go to understanding what's happening, now we're moving into the realm of hypotheses. So a good definition of a hypothesis is a tentative interpretation or an explanation for an observation. And so the way I like to think about observations and hypotheses is that observations are telling me what happens. A hypothesis is an explanation for why that is happening. Now, one thing that may not be obvious, but that good hypotheses should follow, is that we have to be able to test our hypothesis, and it has to be possible to prove our hypothesis wrong. And that may seem counterintuitive, but this is a property of hypotheses that's called falsifiability. And so, in order to have a good scientific hypothesis, it must be possible to make observations when we test it that prove that our hypothesis is wrong. So we have to be able to test it, and for a good hypothesis, we should be able to falsify it. And something that we'll talk about in the rest of this video may also be sort of counterintuitive, and that's the hypotheses and laws and theories, when we talk about those, can almost never be proven to be right. And we'll talk about some examples of that. So when we think about a hypothesis being testable and falsifiable, let's look at a couple examples. So these are some examples of potential hypotheses, and I want to know if they're testable, and I also want to know if they're falsifiable. So if we look at that first one, our universe is surrounded by another larger universe with which we can have absolutely no contact. And so when I ask whether this is testable or falsifiable, and so I'm asking, is this a good scientific hypothesis? I'm not asking, is it right or wrong? I'm asking, is it a good scientific hypothesis? This first statement may be true, it may not be true, but the fact that we can have absolutely no contact with this other larger universe means that I can't test it. And so this hypothesis is not a good scientific hypothesis because it's not testable. And if it's not testable, it's also not falsifiable. If we look at that second one, there are other inhabited planets in our universe. So we can certainly test that, right? We can send out probes to other planets. We've set up radio telescopes, and so we're listening to see if we can find transmissions given off by other intelligent civilizations. So that's certainly something that we're testing. But when we ask about falsifiability, I don't think that hypothesis is falsifiable. Right? We can go to other planets and we can look for other forms of life, but just because we don't find it doesn't mean that the life isn't there. Right? Testing all of the possible planets in the universe is impossible. And just because we don't receive radio transmissions, or we don't recognize that we've received radio transmissions from other sources, and that we haven't yet, doesn't mean that there isn't life on those other planets. And so, while we can test that hypothesis, there's no result that can definitively falsify it. And so it's not a great scientific hypothesis, right? And so this is where things get a little bit gray. Not all hypotheses that we test and that we work on are necessarily great scientific hypotheses, because I certainly support the efforts of SETI. I believe that this hypothesis is probably true. I believe that there probably are other inhabited planets. There is life outside of Earth in our universe. I suspect that's probably true. But as it's stated, that is not a very good scientific hypothesis. Now, we can think about ways that we could maybe state that better, where it would be testable and falsifiable. So an easy way to change it up so that it would be falsifiable would be to say there are not other inhabited planets in our universe. Now, we can test that, right? We can go out and look for life on other planets, so that is still testable. And then all we have to do to falsify it is to find life on another planet. So sort of a trivial way to rewrite that to make it falsifiable would be to say there are not other inhabited planets in our universe. Another way, and that's sort of trivial, another way to make hypotheses better is sometimes to be more specific. So if I was to say, I'm going to build an instrument that has a spectrometer that can detect amino acids, and I can send that to the moon Europa, and I could say, the concentrations of amino acids in the moon Europa are going to be above the detection limit of this spectrometer. Right? And I can go there and test it, and if I don't detect amino acids, then I have falsified that hypothesis. So sometimes being more specific is a way to make our hypotheses falsifiable and to be a better scientific hypothesis. If we look at that third example, so any two objects dropped from the same height above the surface of the Earth will hit the ground at the same time, as long as air resistance is not a factor. And so that's certainly testable. We can drop lots of different objects and we can see whether they hit the ground at the same time. So it is testable. And it's also falsifiable. In order to falsify that, all I need to do is find two objects that don't fall at the same height. And so that would be an example of a good scientific hypothesis. It is both testable and falsifiable. Alright, so I have a quick example. I think determining whether a hypothesis is testable is pretty easy. Falsifiable is a little bit harder. So I have an example here. And what I might recommend is pause the video, think of what your answers are, and then compare them to what I come up with. And so I want you to indicate whether each of these hypotheses is falsifiable. Alright, so if we consider the first one, the Minoans were the first civilization on Crete. So I think that is falsifiable. If we go and find archaeological evidence of an earlier civilization, then we have falsified that hypothesis. If we look at the second one, Minoans were not the first civilization on Crete. So I think that is not falsifiable, right? We can go and look for evidence of earlier civilizations, but just because we don't find any doesn't mean that we falsified that hypothesis. It just means we maybe haven't found the evidence yet. We didn't dig deep enough, or we didn't look in the right places. So I think that second statement is not falsifiable. And then the third one, the Minoans were the best civilization on Crete. Well, what is the best, right? How do we define the best? And so I think this is more of a matter of opinion. And so opinions are not falsifiable. And so that would not make a good scientific hypothesis. Okay, so experiments are how we test our ideas, how we test our hypotheses, or also our laws and our theories. Now, when we're designing experiments, I think one important thing is that when we design the experiment, it should generate observations that can either confirm or refute or falsify our hypothesis. And so that's an important consideration to take into account when we're designing our experiment. Are the observations we make when we run the experiment going to be useful in testing our hypothesis? Alright, so let's talk about scientific laws. A scientific law is a summary of observations that combines all past observations into one general statement. So an example of a scientific law is the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. Right, so as we developed this law, it probably started, or not probably, it did start with investigation of individual experiments. One famous scientist who did a lot of work on this was Antoine Lavoisier. And so he did some very careful experiments at the end of the 1700s where he would very carefully weigh out all of the reactants and enclose those in a bell jar so that the reagents and products couldn't escape. And then he'd run a chemical reaction, and then he'd very carefully measure the masses of all the products. And what he would find is that in these individual experiments, the mass of the reactants always weighed the same as the mass of the products. And so, when you do this for one reaction, that's an observation. But he did this for lots of reactions, and he always came to the same conclusion, along with the work of others. And so, after making many, many observations, you can then sort of collect those and summarize those into a scientific law. In this case, the law of conservation of mass. Now, laws are a lot more useful than observations because they allow us to make predictions. Right? For example, the sun rose in the east this morning. That would be an observation, right? Now, over the existence of human civilization, right, the sun has always risen in the east, right? And so we can summarize all of those past observations into a law that the sun will rise in the east every morning, right? Now, the advantage of that is, the first one, the sun rose in the east this morning, that doesn't necessarily tell me what's going to happen tomorrow or the next day, right? But the fact that the sun rises in the east every morning, right, well, now that's something that I can use to make future predictions, or I can now use the sun in terms of navigation or for telling time. And so the laws, because they allow us to make predictions, are much more useful than just simple observations. But what observations and laws have in common is they tell me what. Right? My observations are my little whats, my laws are my big whats. Right? In the law of conservation of mass, there's no attempt to explain why matter is neither created nor destroyed in a chemical reaction. It just tells me what happens. It tells me that it's not created or destroyed. Alright, so our observations are sort of like little whats, our laws are big whats, our hypotheses are little whys, they're explanations for observations. Well, our big whys are theories. And so a theory is a general explanation for the manifestation and behavior of all nature. Sometimes theories are called models. They are really the pinnacle of scientific knowledge. Right? Laws just tell us what happens, right? But the theories explains why things happen. And so I think a really important distinction to make when we talk about theories is a distinction between what a scientist means when he's talking about a scientific theory, and when we use theory in sort of everyday language, right? In everyday language, a theory is often used to say, that something is not certain. It's like, oh, that's just your theory of the crime, or something like that, right? We're not confident about it, right? But in science, it means something very different. We're not uncertain about theories at all. They are our best explanations. We are as certain about them as we can be about anything. And so a theory means something very different than it does to a scientist than it does in everyday language. The theory, what distinguishes it from a law, is just that the theory is an explanation where the law just tells us what happens. And so the theory that we might use to explain the law of conservation of mass is Dalton's atomic theory, right? And that says that all matter is made up of these tiny submicroscopic particles. In a chemical reaction, I can't create and destroy atoms. We just rearrange how they're connected to one another. And so you can see that theories are often much deeper and require much more to explain them than laws do, which makes sense because theories are telling us why things happen. And so the fact that it takes more to elaborate on those probably makes sense. Now, one thing that I should mention at this point is that just because something becomes a scientific law and it becomes our best what's, and just because something becomes a theory, it becomes our best why, doesn't mean that we don't continue to test them. It doesn't mean that they can't be falsified, right? The law of conservation of mass, that was first proposed by Antoine Lavoisier in the 1780s, and over the next 100 plus years, all experiments that people did seemed to confirm the law of conservation of mass, that matter could not be created or destroyed, right? But then along comes Einstein in the early 1900s and his theory of relativity, right? And E is equal to mc squared, right? And he's telling us that matter and energy are basically the same thing. And in chemical reactions and in nuclear reactions, when we give off energy, that's also giving off mass. And so it turns out that the law of conservation of mass is in fact not 100% correct, right? And when that happens with a scientific law or a scientific theory or a hypothesis, we don't necessarily throw them out. We haven't thrown out the law of conservation of mass. We still use that in chemistry all the time. And it just matters. We have to put limits on it, right? In a chemical reaction, it happens that the matter does change, but the energies involved in chemical reactions are so small that it's not possible to measure the changes in mass. And so for all practical purposes, when we're doing chemical reactions, we can treat them as if mass is conserved. And so we continue to use the law of conservation of mass. We just know that there are limits on that. When we go to nuclear reactions, those involve so much energy that the changes in mass are now much more significant. And so we have to take that into account when we're doing our experiments and when we're interpreting our data. Now, our textbook has a flowchart that sort of illustrates the scientific method. This is not it. This is a flowchart from another textbook. I think if you go to any textbook on chemistry, in the first chapter, they'll have a flowchart of the scientific method, and they'll all be different. And I actually kind of like that because it helps to make the point that the scientific law is not these 12 rigid steps, and it's sort of a flexible method of learning about the world around us. Now, this is the flowchart from our textbook, and I actually kind of like this one in particular. Right, so scientific investigations often start with making observations. Right, we make observations to try to explain those hypotheses. Right, we then perform experiments and make more observations, and if those results are consistent with predictions, then that contributes to our body of knowledge. If our results are not consistent with the hypothesis, then we have to go back and revise our hypotheses. And then we continue to test this body of knowledge. Right? If we find things that don't fit with the rest of our body of knowledge, then we've got to go back and make new hypotheses or revise hypotheses and continue to do testing. And what I do like about this flowchart in particular is because it highlights the similarity between observations and laws, right? So after much additional testing and consistent observations, right, we might be able to summarize all of our observations into laws. And so our observations and our laws are similar in that they tell us what happens. Right, and after much additional support and testing of our hypotheses, we may be able to coalesce those explanations into theories. And so I don't know that it's often true that a single hypothesis ever becomes a theory. I think it's more likely that lots of hypotheses collected together forms a complete explanation that eventually becomes our theory. But I still like this, right? Because observations and laws tell us what happens. Our hypotheses and our theories are significant because they tell us why things happen. There are explanations. And so my final slide in this video is to just sort of summarize kind of what I've talked about, right? So if we were going to fill in this table with some of the pieces of the scientific method that we've talked about, if I wanted to fill in this box here, so it describes what happens and applies to a single or a small number of events, that would be my observations. Right, and if I think about my explanations, but they're my small explanations, those are my hypotheses. And then when I go here, right, it applies to all events, but it tells me what happens. These are my big whats. Those are my laws. And then my big whys, my explanations, those are my theories. And so I really like this chart because it sort of simply sort of summarizes and sort of organizes what these different pieces of the scientific method are and how they relate to one another.